Application of electrolysis. The chemistry of metals is characterized by their ability to donate electrons to form ions. Because metals are typically such good reducing agents, most are found in nature in ores mixtures of ionic compounds, often containing oxide, sulfide, and silicate anions. The noble metals such as gold, silver, and platinum are more difficult to oxidize and are often found as pure metals. The first application of electrolysis is in producing aluminum because although aluminum is one of the most abundant elements on Earth, ranking third after oxygen and silicon, aluminum is a very active metal. It's found in nature as its oxide in an ore called bauxite. Production of aluminum metal from its ore proved to be more difficult than production of most other metals. In 1782, Lavoisier recognized aluminum to be a metal whose affinity for oxygen is so strong that it cannot be overcome by any known reducing agent. As a result, pure aluminum metal remained unknown. Finally, in 1854, a process as found for producing metallic aluminum using sodium, but aluminum remained a very expensive rarity. In fact, it is said that Napoleon III served his most honored guests with aluminum forks and spoons, while others had to settle for gold and silver utensils. The breakthrough came in 1886 when Charles M. Hall in the US and Paul Heroult in France almost simultaneously discovered a practical electrolytic process of producing aluminum. The key factors in the Hall-Heroult process is the use of molten cryolite as the solvent for the aluminum oxide. So the figure shows the schematic diagram of the Hall-Heroult process. Bauxite is not pure aluminum oxide, which we call alumina. It also contains the oxides of iron, silicon, titanium, and various silicate materials. So to obtain pure hydrated alumina, the crude bauxite is treated with aqueous sodium hydroxide. Being amphoteric, alumina dissolves in the basic solution. This is the solution equation. The other metal oxide, which are basic, remain as solid. The solution containing the aluminate ion is separated from the sludge of the other oxide and is acidified with carbon dioxide gas, causing hydrated alumina to precipitate this reaction. The purified alumina is then mixed with cryolite and melted, and the aluminum ion is reduced to aluminum metal in an electrolytic cell of the type in the figure in the previous slide. Because the electrolyte solution contains a large number of aluminum-containing ions, the chemistry is not completely clear. However, the alumina productivity reacts with the cryolite as follows. The electrodes reactions are thought to be the overall cell reaction can be written as the aluminum produced in this electrolytic process is 99.5 pure. To be used as a structural material, aluminum is alloyed with metals such as zinc, which is used for trailer and aircraft construction, and also combined with manganese, used for cooking utensils, storage tanks, and highway signs. Another application of electrolysis is electrorefining metals. Purification of metals is another important application of electrolytes. For example, a pure copper from the chemical reduction of copper core is cast into a large stubs that serve as the anode for electrolytic cells. Aqueous copper sulfate is the electrolyte, and then sheet and ultrapure copper functions as the cathode. So the main reaction of the anode is copper produce a copper with two charge, positively charged, plus two electrons. So other metals such as iron and zinc are also oxidized from the impure anode. Noble metals impurities in the anode are not oxidized at the voltage used. They fall to the bottom of the cell to form a sludge, which is processed to remove the valuable silver, gold, and platinum. The copper ions from the solution are deposited into the cathode, producing copper that is 99.95% pure. Next, we have metal plating. Metals that readily corrode can often be protected by the application of a thin coating of a metal that resists corrosion. Examples are tin can, which are actually steel cans with a thin coating of tin, and chrome plate, steel bumpers of automobiles. An object can be plated by making it the cathode in a tank containing ions of the plating metal. The silver plating of a spoon is shown in the figure in an actual plating process. The solution also contains ligands that form complexes with the silver ion. By lowering the concentration of silver in this way, a smooth, even coating of silver is obtained. Lastly, we have electrolysis of sodium chloride. Sodium metal is mainly produced by the electrolysis of molten sodium chloride. Because solid sodium chloride has a rather high melting point of 800 degrees Celsius, it is usually mixed with solid CaCl2 to lower the melting point to about 600 degrees Celsius. The mixture is then electrolyzed in a down cells, as illustrated in the figure, where the reactions are at the temperature in the down cells. The solution is liquid and is drained up, then cooled and cast into a blocks. Because it is so reactive, sodium must be stored in an inert solvent such as mineral oil to prevent its oxidation. Electrolysis of aqueous sodium chloride or brine is an important industrial process for the production of chloride and sodium hydroxide. Sodium is not produced in this process under normal circumstances because water is more easily reduced than sodium. Hydrogen, not sodium, is produced at the cathode. So chlorine gas is produced at the anode. Thus the electrolysis of brine produces hydrogen chloride. It leaves a solution containing dissolved sodium hydroxide and sodium chloride. The contamination of the solution hydroxide by sodium chloride can be virtually eliminated using this special mercury cell, which is illustrated in the figure, for electrolyzing brine. In this cell, mercury is the conductor at the cathode, and because hydrogen gas has an extremely high overvoltage with a mercury electrode, sodium is produced instead of water. The resulting sodium metals dissolves in the mercury, forming a liquid alloy, which is then pumped to a chamber where the dissolved sodium reacts with water to produce hydrogen. Relatively, Pure solid sodium hydroxide can be recovered from the aqueous solution, and the regenerated mercury is then pumped back to the electrolysis cell. This process called the chlor-alkali process, which has the main method for producing chlorine and sodium hydroxide. Now, among the discussed application of electrolysis, pick one and discuss further this process.